Well, Dan here, your philosopher, mechanic philosopher. Spent many years at the drag strip, racing. Don't want to get too political. As bowler, historian, voter, taxpayer. A friend asked, um, I may need more power. Will the Wermacht return to this country? Well, we don't know. So here we go. If you need more power, this could be for you. There's my friend, Victor. At least he and his brother Herman were able to escape the Wermacht. Let's hope more of us can. Continuing on. So the question is, what do you got to do if you want more horsepower? Well, you want to win the race, you're you're going to need a fuel with a real high heat content that will not self-detonate. Now, you see the idea there is our four-stroke cycle internal combustion spark ignition engine. Basically, well, it's an air pump, and power or horsepower is all about getting things done real fast. So you're not going to want a fuel that provides very little energy. You're not going to want a fuel that will self-detonate, cause knock, because the self-detonation or a knock is an explosion. That's not what you want. We want to push on the pistons with real high compression, and we don't want the engine to break. So we're going to need to get things done fast. We're going to need to operate at high RPM, and again, we're really focusing on the four-stroke cycle engine that most of us are familiar with. Continuing on. Now, actually, well, what is the fascination with horsepower? Well, it's, getting things done. Now, let's think about early man. If he wanted drinking water for his cave or hut, and he had a bucket, he could go fetch it from the river. But what if he lived up there on a mountain, let's say for protection? Well, going out of the river, lugging up all of that water could be pretty heavy. It's all backbreaking work. So now, if he was rich and powerful, he could have animals or even slaves do his heavy work. And we had a movie everybody made fun of, and this creep said that greed is good. Well, I wonder if he was around in the days of ancient man, if he would have said slavery is good, because if you were rich, I mean, that's what you had. You had slaves. You get people to do the work. They didn't have machines around. So somebody figured out they could domesticate animals, and the animals could plow the fields faster, and, so the next thing the horse was more popular than, let's say a weak human being. So, but, if you were king, of course, maybe we got a modern king emerging now here in the United States. And, the hot ticket, he liked to have animals or people, under his control, and he could get a lot of stuff done while sitting on his freaking butt or going to play golf or something like that. Now, continuing on, at any rate. So mining was, of course, a big to-do because as they were doing the coal mining, they found out they could get heat. and with the coal, and that would permit them to do all kinds of work with metals to forge utensils, tools, weapons, all kinds of stuff like that. And now, of course, the mine shafts, like over here, we got a little, I guess that's called like a pit pony. Well, they just wanted to follow the vein, of whatever it was that they were looking for, and so those things could be narrow. And of course, there was a big opportunity back then for women and children to lug coal or whatever it is out of the mines. But then, of course, they came up with the pit ponies, and those animals got the chance to do that. But now, so dragging a weight up a hill is going to, of course, be work. But there was also the idea of grinding things. And you can see over here a nice link. I'm going to say thank you to the YouTuber there that, well, I'll tell you, at the mill. You get a job at the mill. So these horses, they got to walk around in circles and circles and circles all day. And, of course, that took work. But now there was also, when we talk about measuring horsepower, we also have actually somebody figured out, let's see what a horse can do in terms of lifting a weight straight up and overcoming gravity. So that's why this, whether you're pushing, you're dragging, or you got rotational motion going around in circles, and admittedly it is all work. And if you were subjected to a science teacher who told you if you didn't lift something that wasn't work, well, that would be a clown. All right, let's continue on. Now, at any rate, another great link right here. And to appreciate what a horse could do, well, a horse can lift 550 pounds in 1 second. And I'll tell you what, let's imagine you're living in some kind of a semi-high rise. You're on the 18th floor, and you got yourself some 150-pound appliance, maybe I don't know how much refrigerators weigh, to tell you the truth, but let's say it's 150 pounds. Now, let's say you got to bring that up 18 floors. That's a heck of a lot of work. Well, I'll tell you what, a horse with some rigging would just pull that right up the side of the building, 18 floors, again in a minute. So I played a little game over here, and the question is, all right, now, if 1 horsepower is 550 pounds moved a foot in 1 second, or lifted a foot in 1 second, then what would, is this figure here, 33,000 foot-pounds in a minute, the same as 1 horsepower? Well, actually, it is, because we just changed the unit of time. So work is force times the distance, and of course, what are we doing? We're overcoming gravity. So if you, again, if you lift 550 pounds 1 foot, and then, well, I'll tell you what, if you lift to 3 feet, then you've done 1,650 foot-pounds of work. But again, that is not necessarily the measure of power, because power is how long did it take you to get the job done. So as we go down the road, I think we're going to see that, well, how fast maybe can you go down a drag strip or something like that. Continuing on. Now, this guy, he's absolutely great too, and I recommend you watch this. I put the links in here because, well, we should know what the horsepower is, and again, it's a rate of work. We should know the math behind it. But I'll tell you, a couple of things I liked about this particular video. We say Thank You Engineering Explained, is this guy who's pretty good with his math. Again, well, he shows us the horse tail lifting 550 pounds straight up there in 1 second, overcoming the force of gravity at constant. But he also connects, he tells us what can we do with a 200 horsepower car. And, well, I'll tell you what is really good is, well, it could move 55 tons in 1 second if you had 200 horsepower. And, wow, you know, I mean, think about 55 tons. I mean, that's over 100,000 pounds. Let's click on. All right, now, getting back to it and like where some of this stuff came from, the Industrial Revolution, power and movement stuff. James Watt, he came up with a steam engine, and we'll go into the evolution and development of the steam engine briefly. But he wanted a way to show to the people with money that he had a device that could make money for them. See, because he wanted to eat too. A lot of people like that. Now, right here, we got a link that's pretty darn good, and it points out that some people would ask a question. Maybe they were familiar with a steam pot, and you see the lid come up because of the pressure of the steam. And well, somebody got inquisitive, and you know, the question is, can we do something with that? And so there you go. Again, pressure will get things to move. All right, well, we all know that, but still, that's an interesting video. And well, you may also want to watch the history guy. I'm going to thank him because he points out that James Watt was like an artist saying, you know, I got great ideas, I'm doing good stuff, but I'd like to make a living, I'd like to eat. And then when he got rich, selling his idea, you know, the old, the steam engine, people were licensing it. The next thing you know, people were stealing his ideas, and we came up with a patent system, or the people back then, that would protect inventors and permit them to share their ideas and still be able to license their ideas. So that generally helped humanity. And we'll continue on. Now, actually, you're my hero. All these videos are about the first hero engine, and you had some guy, a Greek scientist about 50 after death, who noticed that he could get a container here to spin on a spindle. If you boil water down here, the steam rose up, and this is a hollow passageway. It goes in here, and then you see it's got these jets. And you'd have high pressure in here, atmospheric pressure out here, and then the jets would cause the thing to spin. This thing will spin that way. Right, that'll move counterclockwise. And all of these are, again, well, the question was, well, actually, one of the videos, the guy's got one of these things spinning at like 3,000 RPM. But the Greeks, they sat around and they looked at it, and, you know, but it took a long time for people to realize that maybe we could do some work if we could attach a pulley to these spinning devices. So again, you want to watch them, I would. They're pretty good. Now, and well, again, actually, the horsepower calculation that 550 pounds lifted by the horse in 1 second, was very much a part of a marketing gimmick because, Watt wanted to get people to buy his machine rather than feeding more oats to the horse. So power has been a great marketing gimmick. Here you got I don't know, that could be a Model A, a Ford, a Model T, I don't know. Maybe I should know, but I don't. But Henry Ford said, we'll give you 20 horsepower, 850. That was a long time ago, 120 years ago, but people were putting it out. That was a lot of money back then. Well, let's click on. Continue it on. Now, another thing, though, this guy here, I've always been fascinated with the idea that modern human beings, all of us, children, men, and women, got all this horsepower available to us. You go out to mow the lawn, you got a 3-horsepower engine there. Maybe you want to till the soil, another 3 or 4 horsepower engine on a tiller. And so I've often wondered what the equivalent is of horsepower compared to a manpower. And they tell us that one healthy horse does the work of one healthy guy. Maybe it does about the work of 30 old men. But at any rate, now this link here, Eric Arpianka was actually, well, he talks about the binding between a man and his horse back many years ago. At the time, travel distances were measured in riding days, and you had better take care of your horse. That's why I tell you, if somebody stole a horse, it was serious business, because even many years ago, people wanted to get out of town. Like, a lot of people don't want to go work for Musk with his Wermacht or whatever they're freaking trying to get going here. People want to get out of town. People want to move. So it's all about the old horse, and actually the pollution that has been created through our internal combustion engines. So this stuff is very interesting, and this guy was actually accused, Eric Arpianka, of some kind of biological terrorism or something. Wow. But at any rate, pretty good stuff there from the old University of Texas. Maybe they'll secede from the Union. But at any rate, now, a question might be asked, how do powerful machines affect our lifestyles? Tell you what, for everybody it means more independence. The teenagers love to get out of the house, right? They were going to drive around. Maybe they drove up and down a strip. They're, happy days. You saw all that. They're freaking cruising. But also meant opportunity, freedom, etc. And travel, see new things. And at any rate, there was also a great book. Over here, the argument was going on, what's better, the horse or the little steam engine here? And actually, Tom Thumb, here we are at 1830. This steam engine on wheels is pulling a bunch of passengers along the rails. Now, you want to make horsepower, the question is, why did the railroads have the rails? Well, it's to reduce friction. So if you have a machine that makes all kinds of power, but it's being wasted trying to drag something across like an abrasive or a sticky surface, well, I'll tell you what, your work ain't getting anything done. So it's going to be critical if we ever develop this engine for racing, that we're going to want low friction components because we don't want to waste energy. But at any rate, Top Gun beats the horse. That year was 1830, and actually back in 1807, so you know this. Now, knowing the ropes, if you were a sailor for so many thousands of years that humans took to the seas to travel by sailboat or sailing ship, a boat might go up and down a river, a ship might go across an ocean or traverse long distances. If you knew your stuff, you knew the ropes. 1807, a guy says, you know what? I'm going to take one of these steam engines. And by the way, steam engines, you know, you got a lot of pressure inside the boiler, you know, and they were blowing up once in a while. So at any rate, steamboats were going up and down rivers and doing local shipping duty, so to speak. Somebody says, you know what, I'm going to sail off for Europe in a steam ship. And tell you what, they made the trip, but please think about the following. You're a human being, you know that if you take to the seas, Mother Nature could say, you know what, your sailboat, your sailing ship, ain't going to make it. You know, Mother Nature. Well, here's something that takes you pretty damn quick. Something that took weeks, now it's a couple of days. People, a bond, a fear, or an appreciation of nature was broken by these machines that could do all this wonderful stuff in terms of transporting us and getting us what we want, like pretty damn quick. So you see that there is a component to I want what I want and I want it now, and these machines doing such a wonderful job of getting it for us. Like I want to get down a quarter mile real quick. I had a plaque. Happiness is a low ET. Well, whatever. All right, now let's see. Does the fuel matter? All right, I'm going to go into this very briefly. Look, it was a backbreaking work throwing all this wood. You know, if we've watched our westerns, you know, at some time, maybe you saw people throwing all kinds of wood into the open hole or the fire hole, whatever it was, of our locomotive. Well, I'll tell you what, that wood is going to be used to heat water, and then we're going to get steam out of that to make the thing go. But would coal be better? Of course it would. And so I just need to keep pointing out that the kind of horsepower we're going to get out of our engine is also dependent upon the type of fuel and actually that is used. And there's a variety of fuels that can be used, and we'll be looking at them near the end of this little dissertation that I do for a friend. Now, there's a principle that we all need to be aware of, and it goes like this. If you heat a gas in a container, and over here, that container is well, even case it's a constant volume, but like let's say I warm both of these to 200 degrees Fahrenheit. Well, if that's the case, this smaller volume is going to have more pressure than this one. All right, so for any given amount of gas, it's or excuse me, they're both going to have the same if they're both up to 200 degrees, because it's going to take more energy to warm all of this. But the idea is the higher the temperature of a gas entrapped in a container, the higher the pressure. And all right, so now these gas molecules bouncing all around, they're pushing on one another, and higher pressure. Well, I'll tell you what, if we're going to want a piston to move one way or the other, the more pressure you got, well, it's like really pack them in. Really pack them in. Yeah, we had a a governor, Jim McGreevy, interesting fellow. Big Jim McGreevy. All right. So, at any rate, now, another thing is, if we're going to want to get a lot of work done, I think it's common sense, we're going to have to burn a lot of fuel. So one of the first things that you do if you want to make more horsepower is you get more cubic inches. And over here we have simply the math on getting, figuring out the displacement of the volume of a cylinder, and more cubic inches means more air. If we're pumping more air, we're going to be able to use, or we're going to match it with more fuel. And more fuel, and also high RPM, burn it quick, I'll tell you, you're going to get a lot done. So more cubic inches is the baseline of where we might start from about how powerful, how much horsepower this here engine's going to be able to develop. But there are other factors beyond the cubic inches. My opinion, today's engines in the year 2025, compared to what we had, let's see, 60 years ago, like 1965, I'll tell you, the 1965 engines predominantly, they were effectively, they might make good boat anchors compared to what we have today, because, again, it's a cubic inch, tells us how much air we're going to be able to process, then how much air we can process, well, how much fuel, we got to match that to the air going through the engine, into the engine and out. You know, so if somebody says to you that internal combustion engine is an air pump, yes, it is. You got to get it in, but remember, you got to get it out. If they say that it's a heat engine, yes, it is a heat engine, because what we're going to do is we are going to burn fuel to heat a cylinder so that high pressure eventually gets developed on a piston, which we're going to connect to a crankshaft, push it down, get it going. So if you would, please check out these sites on YouTube, and God bless. I tell you, I think we're very lucky to have a lot of information available if we want it. So, yeah, every once in a while I look right at the camera. I'm simply looking at the computer screen so I know where I am and do this. Now, here's an expression now, the air charge. And I'll tell you, charge is a great word. And here we go. I got a nice little definition of it. A charge, well, they're saying it's obsolete to put a load on. Actually, the force of gravity gives air, and air is matter, but is what state of matter is air in? Is it a solid? No. Is it a liquid? Nah, not really. No. Is it a gas? Yes, it is. So it's a vapor. Now, by the way, there's two types of fluids: liquid fluids and vapor, or gaseous states. But at any rate, now, so with the force of gravity, actually, the weight of air is here at sea level is a lot heavier than if you went up the mountain. So a full load on an engine happens when you open the throttle. Now, by the way, a gasoline engine is air throttled. You open the throttle, bang, you got a full load there on the engine if you're low RPM, because it's time for all the air to get in. So at any rate, good definition, full load, like full volumetric efficiency, easy to obtain at low RPM, because you got plenty of time for the air to go through any restrictions that may exist and get in there on full charge. But now also there's a beautiful expression for uh, uh, a full charge, or you see, a load or a burden are given a task. A nurse is charged when God, I believe, charges us with responsibilities, blessings. Uh, it isn't for us to sit around and eat grapes on our butt at the orgy, or to spend all day freaking golfing. Blessings, responsibilities for the well-being of others is a charge, I believe, from God to be decent, try to be a decent person. Uh, Now, some people, of course, like if we look at our healthcare system, they figure it's an opportunity to take somebody else's suffering, deny their claims, keep all the money they've been paying for insurance, privatized insurance. What a freaking disgrace. All right, but anyway, now, cubic inches, supercharged. All right, so that air charge into the engine, you open the throttle, I tell you what, somebody is not satisfied with the cubic inches they got, they could add a thing called a supercharger. And that supercharger is going to like pack them in, you really want to pack them in. Now, but the thing is, a normal gasoline engine does not have a supercharger or a turbocharger on it. It's simply the opening of the throttle and Mother Nature's air pressure, boom, gets as much air in there as the valve train will permit. So first the throttle makes a decision, but then the question is also going to be, do the valves in the engine that affect when our strokes occur? Are they going to let enough air in? All right, so now, again, let's remember we need a lot of air in there to support combustion, because air is 78% nitrogen, 21% oxygen, 1% other. Maybe somebody let something go or something like that. Now, at any rate, over there you got another link, Real Engineering, and I like this one because it talks about, an early inefficient engine, the Newcomb engine, way back in 1712, and actually, what makes the piston move? I'll tell you what has happened here is they're going to burn some fuel down here. Now, maybe if they're near a coal mine, they're going to use coal because it's readily available. Let's give this a click. We'll move on to the next one. Okay, so now, we're going to burn some coal or wood or something down here, get some water boiling away. There we go. Now we got steam. We got steam pressure. So that's above this boiler. It's above the pressure of gravity. Steam pressure is greater than air pressure. And we're going to open a valve, and the steam is going to push this piston up against the force of air pressure. Now, gravity, I think you're going to say, well, yeah, you got gravity pulling the chain down or whatever they got over here. Yes. So we are at now a point where this piston's way up. This thing has gone down into the mine, and steam is again pushed up against the force of gravity. Let's go down. All right, whoops. All right, but now the thing is, when this thing was way down, the chain was way down, goody, but we're going to want to lift something up out of the mine. So here's what they did. This area had really been heated up by the steam. So somebody comes along and they cool this area. And as they cool this cylinder, the pressure here drops. They've got the valve closed, so the steam pressure can't be working on it. So you got a low pressure area here, you got a high pressure area here because, well, why? Because you got air pressure pushing down on here. So the air pressure pushes the piston down, and when that happens, as you can see from this mechanism, this chain is going to pull up. Wonderful. Now they're getting something out of the mine. But I think that really what I wanted to point out is to not underestimate the power of air pressure. You know, anybody that's ever heard like a thunderclap, knows, bang, air can make stuff move, and even normal air pressure. Now, you may want to look into what are some of the typical units of measure for air pressure. You got PSI. They will often say that air pressure at sea level is about 15 PSI absolute. You got barometric pressure, which is often measured in inches of mercury. And about 2 inches of mercury is about the equivalent of 1 PSI. So the weatherman talks about how, you know, the air pressure's around 30 inches on the barometer. All right, so there's a lot of different ways of measuring. And also, engine vacuum is a way of measuring the pressure in an intake manifold below atmospheric pressure. See, because our running engine on its intake stroke is going to create a void that is going to cause, well, it's going to be creating a low pressure area so that air can push, air pressure can push more air oxygen into the engine. We'll click on. Now, at any rate, somebody figured out that back and forth with the chain was pretty inefficient, and it was. And they laid our steam engine on its side, and we're going to get some rotational action out of this thing here. And they got valves. First, we got steam pushes on one side of it. Then, because of the valving, the steam will push on the other side, so we're going around and around. Or wait a minute, let's add a flywheel, because this back and forth was kind of like sluggish. But you can add a flywheel if you want some, let's say, power ahead of time. It's a little bit of a trick. So if we're going to spin, you get a flywheel spinning, a 90-pound flywheel spinning at real high RPM. When you're going to launch a drag race car, come off the line, you pop the clutch, and I got to tell you, that is some launch when the drivetrain, the clutch and the transmission and the rear and all that connects with this thing that's spinning like at 7,000 RPM. Boom! The thing freaking takes off like a rocket ship. But also the flywheel will smooth out many of the vibrations from the back and forth. All right, let's just continue on. All right, now at any rate, I also, well, again, we're really talking about, or I'm supposed to be talking about, the internal combustion engine. But there's also something else called external combustion engine. And I'll tell you what, these guys, Muhammad and Ahmed, or Ahmad, they do a great job with the written word, and I just want to thank them for their effort. And they're pretty thorough. They go into a lot of detail on how the locomotive works. And by the way, steam engines, or steam is still used in industry for many applications, you know, like it works. And it's a great dissertation. By the way, the reference, steam traction, Uh, well, it's great to talk about making horsepower, but an engineer will tell you if 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 the rubber doesn't meet the road, you ain't going anywhere anyway. So traction is an expression of that engineers will use for getting a force applied to do some kind of a job. And by the way, the fire hole of the door right here, if you watch your appropriate number of westerns, that's where they're throwing all the coal or all the wood is going into this fire hole. This here fire brick arc, I'll tell you what, actually the intake, there's a grate down here that catches all the coal or all the wood, but air is permitted to come up. The intake is down here. And uh, this area here is where we're trying to cool it, that we're trying to heat. And you wouldn't want cold air just blasting straight up there. So what they would do is, well, they put a little something there to block or prevent the cold air from hitting the water on this area of the boilers that they're trying to heat. So it was like a deflector, you know. We'll go quick. All right, so now, and also these guys, by the way, uh, well, we want to make all this power. Well, picture your locomotive and the rods going back and forth, back and forth. And the actual working cylinders of these locomotives would be up near the front. And then the piston would be connected to like a connected rod. It's pushing back and forth to turn linear motion into rotational motion. And these guys, they give us a nice, now by the way, they also saturated steam, just so you know, is steam that was in touch with boiling water. Superheated steam is this here saturated steam that's been reheated or heated even more, and a high pressure. You can get a lot of heat, a lot of pressure. By the way, heat goes up, pressure goes up. Pressure goes up, heat goes up. Ooh, nice little cycle. And it's pressure and balance that gets things to move. So at any rate, we got high pressure coming in here, boop, boop, pushes the piston that away. I think. Yes, it does. All right, but now this here rod here is like valve timing. And then what it's going to do is when it moves this way, well, then I'll tell you what, the high pressure coming in can get over here and then push the piston, bang, the other way. So let's click on, and but well, you got to just we thanked them. So at any rate, and also let's go up is get some nice stuff there. Chug chug. Here's the piston up. Now you see all these levers that we got this cam timing here. That's effectively a valve, cam timing, but also pushing back and forth, turning linear motion into rotational motion is complicated and actually a bit wasteful. So that's something we want to have in the back of our minds as we continue on. Again, we want to turn linear force into rotational force, and watching these old steam engines at work could be a lot of fun wondering about that. And by the way, how big are these pistons? The pistons, look at that. That's one of them. These pistons are a couple of feet in diameter anyway, and I mean that's really pretty big, and it's just wow on piston diameter. There's all kinds of unbelievably huge pistons, and we'll continue on. Uh, and let's see again. Oh, by the way, I'd like to thank Internet Archives. They accept donations. I've donated to them and joined uh, all kinds of real good stuff. You know, there are people who want to profit off of the body of human knowledge rather than letting us share in it and the joy of discovery and learning and all of that. Oh yeah, that's you can see my Perot thing back there. Yeah, I was a big Perot fan. Uh, he might have been nuts. I don't know. I think he was, I guess. But even though I liked him at the time, but what could I say? All right, so at any rate, again, why the rails? Well, whether you were dragging something at an angle, like a vector, move up to overcome gravity, or the rails reduce friction. And if we want things to move easy, well, we got to reduce friction. And of course, oil in an engine helps reduce friction. The proper clearances reduce friction. All right, let's continue on. Now over here, I happen to love this demonstration, so if you're watching this, you're getting hit with it. Compressing a gas will cause its temperature to rise. And here's what's going to go on. This little rod here has got a couple O-rings down here. This is a cylinder. Guy's going to take a cotton swab, take a little cotton off of it. He's going to put it in here, and he's going to push down on it. All right, and when he pushes down on it, you're going to see that the cotton actually burns. So in other words, just compressing the gas is enough to initiate burning. And now, by the way, combustion is burning. Combustion, it's not an explosion. If somebody calls it an explosion, I'll tell you what, do you want your engine to keep running and go down a road? Yes or no? Yes. If you want it to explode, well, I'll tell you what, you ain't going to go down the road. All right, so this guy, he talks a little, well, he's pretty good. Adiabatic processes mean that there is no heat loss. Now, a diesel is a compression ignition engine. So, in other words, the diesel relies on the heat of compression alone to cause burning to start happening. I just would like you to know that. All right, now these guys with the fire syringe, they're having a nice little chat, and they're real sporty fellows, and I hope you enjoy them. I want to thank them for their efforts on helping us understand. Now, because also they do a thing where they compress it slowly, and the cotton doesn't burn, the fire doesn't start. And actually, slow compression would be like, imagine your engine's turning slow in the morning. It doesn't want to start. Well, maybe it's not making enough heat of compression to get the fuel burning, whether we got spark ignition or not. So in other words, just putting a spark in a cylinder, I'll tell you what, if conditions are not right, if there's not some heat there, you're not going to go too far. So let's click on. Now this guy, Warped, all I say about him is Warped, he does a whole bunch of experiments with this thing of just compressing air with a little bit of cotton or some paper or something in there. And he's pretty wild. He tries hitting it with a sledgehammer, and then we see the cylinder blow up. You may want to watch him. He's like a lot of fun, too. We'll continue on. Now, we're going to review. Now, I have to admit I've gotten off track, but you see, the thing is, if we're going to talk about making horsepower, you may want to know where it came from, what it tries to measure, like a rate of doing work, why we had it. It's actually to get people to buy stuff that's going to do a lot of work. All right, now, but are we focusing on IC, internal combustion, SI, spark ignition, and Do we want a fuel with a lot of heat value in it? BTU. Our fuels are usually related in BTUs. All right, now, you should know how much oxygen is available because it is oxygen that supports combustion. 78% of our air is nitrogen, which is inert. It doesn't do anything except take up space. Are there people in your life who do nothing other than take up space? Well, there's people in my life, well, there's some that make me sick. One of them's in the White House. He's a freaking shit. Now, let's see. Lots of compression pressure. Now, our engine is going to want a lot. When the piston's coming up and it's squeezing all that air and the combustible mixture together, we want a lot of pressure because I'll tell you what, if we start out with a lot of pressure, like a big bank account, the freaking jerk there, his father gave him hundreds of millions to get started. Oh my God. You know, that's a nice start. The rest of us would like that too. All right, but at any rate, you start out with a lot. Tell you what, when we have combustion, we're going to get a heck of a lot on a power stroke. So high compression is good. High compression alone. Lots of air, lots of high energy fuel, high heat content fuel, lots of compression. All of that goes to making power. And by the way, you're going to want your engine to be warmed up if you want full power, because a warmed up engine is going to seal better when it's supposed to be sealing on a compression stroke. Oh yeah, your low friction components, it's common sense, you're going to want what? A lightweight but very strong. So those are going to be expensive components because, well, I tell you what, everybody knows that it's easier to accelerate something that's light. And there was a famous drag racer, Don Gartless, who said, it's difficult to accelerate a freight train. And so, in other words, the rails that you see at a drag strip, they're made to be as light as possible. All right, now, so, if we're designing that engine, first factor is probably going to be displacement. Bigger engine can probably do more. Now, we're going to be looking at some cylinder heads. They got different designs of cylinder heads to permit more air in. And then we're going to also look at intake and exhaust manifolding. Again, to get that air in and out. You know, you can have 427 cubic inches, but if the air can't get in, that doesn't do you any good down the cylinders. So now, also there's the camshaft establishes how far open the valves go in order to let the air and fuel in and to let it out. And when the valve timing events occur is going to affect the performance or horsepower of your engine. Have you ever heard an engine that it wasn't stalling out, but you listen to an idle? Vroom, 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 vroom. You might be listening to something like in a motorcycle, a three-quarter race cam, and that's going to be a camshaft that at low RPM, you know, it ain't too good. But you get the revs up, and that thing's really pumping a lot of air in and out. And of course, turbochargers and superchargers also improve volumetric efficiency. All this stuff after the engine size is all meant to improve volumetric efficiency. Let's go on. All right, now, the throttle. Is a gasoline engine fuel or air throttled? So when our beauty here steps on that gas pedal, what's she letting in? Well, she's letting in the gas, but it's not the fuel in the tank, it's the air, atmospheric pressure. So, and by the way, we only make horsepower, serious horsepower, at wide open throttle. So it's pedal to the metal, and, well, that's what's happening. So the gas pedal is a gas pedal, not a gasoline pedal. Now, you want to make horsepower. You're going to put your engine on a dyno. It'll measure horsepower. Well, where do you want your dyno? Do you want to have it up on the top of Pikes Peak, or do you want your dyno to be down here at sea level? Well, I'll tell you what. This little chart here says at sea level we got about 14.7 psi absolute. Up at Pikes Peak, it's only 8.6. And what that's telling us is actually, whether it be the pressure or volume, the fact of the matter is there's a lot more oxygen available at sea level than there is on the top of a mountain. So you should know that. And drag racers, I'll tell you what, if you had a drag strip up in the mountains, you got to recalibrate everything. It could be dangerous racing up there, and the car ain't going to go so fast because there's not much oxygen available. And years ago, when we had carburetors on the car, you might see a sticker that says, this car climbed Mount Washington or something like that, any of these big hills, because if you had a carbureted vehicle, the carburetor was designed to provide like a lot of fuel, maybe in St. Louis, New York to St. Louis. But when you got up at high altitudes, the thing would start running rich. And when it started running too rich, it had plenty of fuel, but you see, it didn't have enough air. And without the fuel injection computers, the brains of modern automotive technology, and you'd have drivability problems. Forget it, Pikes Peak. So let's continue on. Now, just so you know, this thing was a 4-barrel carburetor. These things are Venturis. When air flows through a Venturi and it speeds up, something happens there. The pressure actually drops when the air speeds up. Now, if you got atmospheric pressure pushing on fuel in a bowl here, and then you got a low pressure right here, and by the way, down the base, you got the throttle plates. They'd be open up. So the throttle plates open up. A lot of air pressure from up here is pushing in. But when it flows through these Venturis, there's a pressure drop. And I'll tell you what, that pressure drop here, you got air pressure working here, you got an airflow going this way. Fuel, atomized fuel with discharge into the airstream going into the engine. And that's the way yesterday's carburetor worked. Now, the old fuel tank supplied liquid fuel to a fuel pump, and a fuel pump pumped that liquid fuel up to the bowl of the carburetor. But it became the job of the carburetor to make sure that the fuel going into the engine was highly atomized. Now, by the way, fuel injectors did a great job of helping the fuel go from a liquid state to the atomization. The droplets were so fine, it was the fuel readily vaporized the rest of the way once it got into a warmed area like an intake manifold or a cylinder. We'll continue on. Now, again, yesterday's carburetor is so you know. First step in turning a liquid fuel into an atomized fuel, which hasn't been vaporized yet, was you could mix air and fuel. And then, so in other words, like some of the spray stuff, spray things, all right. So that's what we're doing. We're mixing air and, et cetera, getting it to atomize on its way to vaporizing. And by the way, we really want vaporized fuel. That's what gets the job done for us in our internal combustion engines. All right, now, and what's going to aid vaporization? I'll tell you what, heat. So your engine probably runs better when it's more efficiently when it's warmed up. Modern engine designers, they do such a good job. We don't even appreciate uh, that while the engine's ice cold, it really is not a good time for the environment or the engine. And I'll tell you what, many intake, well, it also reducing the pressure uh, on the liquid helps it to vaporize. So heat and low pressure help liquids vaporize. And we want to run on we want vaporized fuel. And we'll continue. Now, uh, our fuel delivery, the job of all fuel delivery systems is to match the fuel delivered going into the engine to the quantity of air. All right, now, yesterday's carburetor at the Venturi area, we discharged some highly atomized fuel into the intake manifold, and that was our throttle plate. If we were idle, it was closed. If we are get up and go, it's drag race time, the thing might be at wide open throttle, so it'd be up and down just like this. Now, here's our intake manifold. There's our intake valve. This is going to be the exhaust valve. Here would be our problem, especially on a cold engine, that when this fuel hits cold, what would it do? I'll tell you what it would do. It would condense. It would turn back into a liquid. Very bad stuff. And yesterday's engines had to do a lot of, we had to do a lot of things like heat riser valves, etc., to get, to prevent or overcome that problem. Now, when somebody came out with port fuel injection, these injectors well, the fuel pump on an old car might put out somewhere between 4 and let's say 12 psi of the liquid fuel going up to the carburetor bowl. These port fuel injectors typically ran at 40 psi above atmospheric. So the pressure gauge read 40 psi, but really it's up to 55 psi, but whatever. There would be a little nozzle in here, and when electrically these things would be commanded open, the fuel would squirt out, and it was really well on its way to being really vaporized. And they would position these port fuel injectors, point them right at the back of the intake valve, because if you're going to put the fuel in, you want it to make it. Oh, by the way, there were some throttle body injectors where Detroit always, the dollar bill, they just took the carburetor off and they put a thing called a throttle body fuel injector right here that did that same job. All right? So that was a throttle body injector. And then they said, nah, we want to get rid of the intake manifolding problems. And we're going to want to point our injector right at the back of port fuel injectors. First multi-port, if you had a V8, 4 of them would fire. Then the other 4 would fire 360 crankshaft degrees later. but then they had sequential port fuel injection where each injector would fire, I'm going to say, on the intake stroke. So if you had 4 cylinders, 1, 2, 3, 4 firing. If you had 8, 1, 2, 3, 4, 5, 6, 7, 8 in the order of the firing order of the engine. And well, I'll tell you what, eventually now we have a lot of gasoline direct injection where we know that this area here, the combustion chamber, or we're in the cylinder now. And again, there's our intake valve, there's our exhaust valve, there's our piston, our connector rods down here. We're right in here. I tell you, squirting into the fuel, forcing it into an area that's already warm, and we can do it, is really going to assure that the fuel is highly vaporized. And highly vaporized fuel is where we're going to get our most power from, by the way, and our lowest emissions, and our best fuel mileage. So we're going to continue on. Here we go. All right. So now, a look at an old carburetor. Again, the job of these carburetors was to match the fuel that they were discharging into the airstream to the amount of air that's really going into the engine. This was a single barrel, this was a 2 barrel, then we had 4 barrels, you know, you go on and on. Now, these things, I don't know if you really can see, but they got all kinds of levers and adjustments. Oh, man, I'll tell you. So, when I was a young guy, I'd rebuild carburetors all the time, and hey, the people would say, oh, that's wonderful, you know, a car used to have a flat spot, now it's good, you really fixed it there, and you're so wonderful, all this. So in other words, my mind was full of useless information, so everybody thought it was wonderful, but, you know, if you needed some rods on your carburetor bent around, I was the guy to say, fuel injection, I think, is much better. Let's go. Now, I tell you what, and we had all kinds of intake manifolds. Again, you got to get the air in. Dual plate intake manifolds provide equal amounts of air fuel to the cylinders. Now, actually, these V8 engines, they could be so convoluted that we were not getting the same amount of air and fuel into each cylinder. And really, if you want a high-performance engine, you want all the cylinders to be doing effectively the same thing. They should all, well, you know, they should all be the same, not varying all over the place. I'm just going to continue on. Questions they are asked. All right. Now, I'll tell you what. Now, also, this thing, variable inertia charging system. Again, if we know our English language, we know where the expression charge comes from. And so, we can tune. If you've ever heard somebody play a wind musical instrument, how about an organ, the bagpipes, whatever you want, you know that there is such a thing as, well, air flowing through something can also be affected by the tuning of the pipes. And there's an expression on the pipe means that your manifolding in and out of the engine is just right for a given RPM range. And of course, the piston and the cylinder constantly going up and down. We got valves constantly going up and down. So we got air moving back and forth, back and forth, back and forth. If you get the timing of that stuff back and forth right, I'll tell you, you can get it so air really charges in when the intake valve opens in a right RPM range, and actually at the exhaust valve, when the exhaust valve opens, that there's a low pressure wave in the exhaust that'll actually help suck a lot of the gases out. At any rate, the right size of this plenum. The manufacturers are not jerks. They figured out a way that well, I'll tell you what, they got a little torque chart up here, and they're showing that without this device, torque is down over here. But they can add this device, and now they got more torque while still letting plenty of air in for the high RPM range. See, this up here was going to happen anyway, but boosting RPM in the or torque in the mid-range is a benefit of this variable inertia charging system. So in other words, you got more power throughout the RPM range. Let's continue on. Now, by the way, I had talked about yesterday's nonsense, a carburetor. And the state troopers, I'll tell you what, they wanted plenty of power when they were in the 4,000 RPM range, chasing somebody at like 80, 90 miles an hour. And they had these cross-ram intake manifolds, fuel flowed all the way from there to here to actually be getting more air in that range, the 4,000 RPM. But so over here, carburetor, so air flows in, mixes, some fuel gets mixed with it, makes a trip over to here, then it's out to the cylinder, and they got another 4-barrel carburetor over here, doing the same for that side of the engine. Well, what's this? That's the exhaust. Yeah, those are the exhaust pipes coming out. What's all of this plumbing? All of this plumbing is they're running heat from the exhaust up to the intake manifold to do what? To warm the intake manifold so that the fuel does not recondense and go back to a liquid. So that's the kind of nonsense they used to have to put up with all these carburetors and all that manifolding. Again, modern fuel-injected engines, they come overcome all that crap. All right, so at any rate, the carbs are gone. We got throttle body units. And on a throttle body unit, you got a throttle position sensor to tell the computer where the throttle is. You know, you got an idle air bypass valve that helps control the RPM of the engine. Like when it's cold, you see you hear your engine's running fast to help itself get warmed up. You got a thing, and then when it slows down or you put the air conditioner on, you're at idle. Are you in neutral or are you in park? Are you in drive? Are you in reverse? What gear are you in? Is the air conditioner on? Yes or no? All affects the idle speed that we're going to want. And I'll tell you what, like this one over here, MAF sensor, mass airflow. How much air is going in? So besides opening the throttle, which is your command, well, how much air is going in? The onboard computer, fuel injection computer wants to know that. We're going to click on, brothers and sisters. All right, now, again, if we're wanting to make power, well, again, how much air can flow in, and different types of fuel injectors. Well, I'll tell you what, this engine's got 2 intake valves. If one intake valve is good, maybe 2 is better. I'll let you know what that's about right now. Actually, if you got one big intake valve, it might weigh a lot. So getting it to reverse direction ain't so easy because it's big. Maybe what we could do and still let plenty of air in is have 2 smaller intake valves that are letting in even more air than just the one big one. But it's easier to get them to change direction without breaking engine parts and heavy valve springs. You know, see, well, at high RPM, uh, the weight of the valve, opening and closing, well, I'll tell you, it just got pushed open. I'll tell you what, now it can tend to say, look, you pushed me that way, I'm going to keep going that way. We would get a thing called valve float. We would need to have very high pressure valve springs to control, to assure the proper closing of the valves. So if we could do something to get these, to overcome or control inertia, get the valves to close easier, well, maybe two lightweight intake valves is better than one big one. Let's click on. Now, all right, there we go. There's a port fuel injection. This is a decent picture. So somebody did a cutaway and got a nice picture. That fuel is well on its way to being vaporized. There's the port injector squirting right at the back of a low friction rocker arm, which is pushing this here valve open. That's a roller right there. All right, and let's continue on. Whoops. Well, at any rate, I'd like to thank Wikipedia, and I apologize to whoever put this one together. It's pretty good. Over here, we got it. Well, on an intake stroke, piston goes down. Intake valve is open. All of this stuff enters. Next, compression stroke. Crank is rotated clockwise. Both valves are closed. We're pushing up. Now, I'll tell you a little before top dead center, right around here, that spark plug fires. And then you got burning on the power stroke. Both valves are closed. Is going to push this here piston down. All right? And so there's our power stroke. So we got an intake and compression and an exhaust stroke, just so we can get to having one super duper power stroke. Over here, well, I'll tell you what, the end of the power stroke happens out here. Now we're going to push up on a cylinder, and the exhaust valve is going to be open, and we're going to push the burn gases out. Now, by the way, burn gases do not support combustion because we've already burned up and used all the air. So over here, we got our intake valve here. This is the exhaust. Wikipedia's got this nice animation. Now, by the way, I thank you, Wikipedia. I've donated to them too because they do wonderful stuff again, promoting human knowledge, the exchange of information, truthful information, and God bless them. All right, continuing on. All right, now, we should know what the expression TDC is. Top dead center. So when that piston's all the way up, that's top dead center. The piston, connector rod, crankshaft, everything is effectively straight up. All right? Some comments on the intake stroke. On the intake stroke, a naturally aspired four-stroke spark ignition engine, the piston's moving downward. That creates a low-pressure area, a void or a vacuum. Air pressure from the outside is pushing air in, and it's going to push in as much air as your intake manifolding, manifolding system allows. It's going to push in as much air as your camshaft. You see the camshaft up above spinning around? There we go. You know, this is a dual overhead cam engine there. We got a real hot rod. And, you know, and the cam is also going to affect how much air can actually get in. Let's click on, brothers and sisters. Compression stroke. Well, I'll tell you what. Before top dead center, let's find out what that. piston is moving toward the top of the cylinder, volume is reducing. If volume is reducing, what is happening to the temperature and the pressure in the cylinder? You let me know, all right? And I'll tell you what, let's continue on that compression stroke. This is a spark ignition engine, and I'm going to let you know, somewhere before top dead center, the spark plug is going to be fired. That's called ignition timing. And it's going to happen while the piston is still coming up because burning takes time. Again, combustion or burning in a cylinder is not an explosion. An explosion is incredibly instant, fast rise in pressure. What we want is a controlled, a burning, a slower rise in pressure. All right, so now let's see. Intake valve finished closing right after bottom dead center. We're on an upstroke. Pressure, temperature rising. Well, yes. Now, let's see. Spark plug gets fired. The burning process, which takes real time, is going to begin. And the timing of the spark is going to be dependent upon a number of factors. Pressure in the cylinder, the fuel being used, the air-fuel ratio of that fuel, and let's say, and now also the RPM, because burning takes place in real time, but naturally, if the RPM of an engine goes up, it doesn't affect the world nuclear clock on a clock on your wrist, but events in the engine are happening faster. So there's a difference between real time and engine timing, which can often be talked about in terms of RPM. We'll continue on. Now we're going to have a power stroke. Now then, ATDC after top dead center. All right, now, our power stroke, we're going to say that the piston, rod, crankshaft assemblies have all rolled past top dead center. I'll tell you what, if they didn't roll past top dead center, they would have got hammered and you find yourself with a lot of broken engine parts around. So they rolled past top dead center while combustion gases, pressures, working pressures were rising. And actually the goal of all ignition timing is to assure that best power and peak pressures for whatever it is you want your engine to do are occurring about 14 to 17 degrees after top dead center. And that's because now this is where we get this whole thing. Why were we looking at freaking locomotives back and forth? Because of those linkages, those rod angles. See, the piston's doing linear motion, but we want to convert all of that into rotational motion. And I'll tell you what, the issue is going to be at what angle is that connected rod, which is connected to a piston and a crankshaft. At what are the angles between the piston, the connected rod, and the crankshaft? And those angles are going to affect really how efficient the engine is in transmitting torque from the power stroke, turning it into rotational energy. Now, as a curiosity item, so you know, typically we know that we can open the exhaust valve while we're still on a power stroke. Now, why do we have to do that? Well, because getting these physical things, these heavy things like an exhaust valve, to open is going to take time. Just like it's going to take time to close it, it's going to develop inertia. Uh, but so also, uh, we can open the exhaust valve 50 degrees before bottom dead center. Well, if we can do that, what does that tell us about combustion or power stroke pressures? Are they all used up by that point? Well, I'll tell you what, I think they are. That's what the message is. Saying we want all great hot rodders to know that. Uh, just so they know. Continuing on. Now, then we got an exhaust stroke. All right, bottom dead center. And BBDC is before bottom dead center in engine language, you know. If you're at the drag strip, you want to know all your nomenclature. All right. Near the end of the exhaust valve was open. Uh, now, by the way, uh, on real old engines that didn't even have an oil pump, uh, or at least not one for the crank and the rod bearings, they actually had spoons on the bottom of that connecting rod cap. That's the thing it's the bottom half of that big end of the connecting rod, and when it would dip down into the oil, uh, it would actually force some oil up to the crankcase. All right, but anyway, look now. Uh, we talked about the exhaust valve. Oh yeah, the intake valve. Uh, this guy over here is going to begin to open while the piston is still coming up. And so there's actually, and again, we actually start opening the intake valve on right before the end of the exhaust stroke. And so that's going to be a period when the piston is right near top dead center. The intake valve is open a little bit. The exhaust valve has not yet finished closing. The exhaust valve actually finishes closing on the intake stroke. Uh, Again, airflow. Oh, hey, get on the pipe. Well, what are you talking about, get on the pipe? And well, actually, I'll tell you what. Uh, Before we talk about getting on the pipe, let's get a little review of some of the math on the torque. And actually, I'm not much of a mathematician or an engineer. So a lot of this stuff, many years of hot rod, I learned this stuff kind of slowly. But I'd like to thank the Khan Academy for a nice dissertation on torque. You could go to YouTube to find out about pedaling a bike. And I'll tell you what, over here in the Science of ABC, I like because they teach us about torque by talking about anybody who's got experience with a merry-go-round. You know what it's like if you want to push a merry-go-round. I mean, where do you push on it? From the outside or near the inside? You know, it's going to be near the outside. So we want to understand what the torque thing. Now also there's a guy donut again making the shaft turn. Uh, he if you'd like to watch this, please do. I'm just going to say thank you, Donut. I found him on YouTube, and I'll tell you, he's really pretty good. He describes torque as a grunt and horsepower as a scream, and I'll tell you what, if you want to get a lot of work done fast, horsepower is a rate of work. When you hear these engines screaming, boom, 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 that's, I'll tell you what, that's many power strokes happening very fast. And so that's like screaming. Now, I would think, in my experience with torque, whether it's loosening something, tightening something, making anything turn, riding a bicycle, that if I want to transmit maximum leverage or energy or power, it would be right about here. The piston's coming down on the power stroke, and right around here is when I'm going to exert the most force. I think that's common sense. You can see it. The distance from the center of the crankshaft to the center of the connected rod throw is going to establish what the total stroke of the engine is. When this guy and this guy are like that, straight up and down, and then again, when they're at bottom dead center, they're up and down again like this, it's still here. You double the distance of the connecting rod throw, and you've got the stroke of the engine, and that can be called the rod throw. Let's click on and see what we got next. Okay. We want max pressures to occur around 14 to 18 degrees after top dead center. This piston's being driven down now. We are on the power stroke, and actually peak pressures are pretty well the heck up. But as you can see, this piston is really being pushed this way, follow the arrow. But the crankshaft's over here. You know, it's like, it's the design of the engine. Again, we would think that this would be ideal. See, so, but you can't always have, well, actually what's happened between here and here is we have used up much of the combustion pressure, heat, whatever you want to call it, or the force has been expended, because maximum pressures in this here sealed chamber occur when it's small, like when the piston is up. And as it gets pushed down, what's happening to pressures there? They're being used up. See, so actually, max power is being occurring when the piston's up around here, if you see it on the mouse, and when it gets down to here. So, over here, again, I try to make the point of this connecting rod angle is a big to-do. It's something to know about. It's a subtle, but it has a lot to do with making power. See, really, if I want to make this crankshaft rotate clockwise, I'd really want to be pushing from here with this red angle, which you drew in there, rather than pushing from up here. And again, it's just, well, this is the closest we get to be the perfect rod angle, but we've already used up all kinds of power. All right, so let's click on. And again, I'm going to thank Donut. He did a really great job. All right. The process of converting linear applied force to rotational is less than ideal. We've said that. Now, what I would like to say is that if you've heard of the Wankel or rotary engine, Mazda with a rotary engine, there was somebody actually tried to cause the shaft that we want to have rotate, this guy, more in line with the combustion pressures that are working upon it. And again, so that was the purpose of the Wankel or the Mazda rotary engine. I just want to mention that because those things have been taken to the drag strips. Click it on. All right, simple question. And what would happen if peak combustion pressure occurred before top dead center? So we're trying to go up, and we have peak pressure. Well, I'll tell you what, I'm going to give you a hint. You'd probably find yourself breaking a lot of parts, and you might hear the engine pinging or knocking if you don't get that done. So if you're getting a terrible knock or ping or rattle out of your engine when you try to accelerate, well, maybe you got some kind of an ignition timing issue. We'll click on now. What would have occurred at top dead center? I'll tell you what. If the peak pressures are right here, the engine wouldn't go anywhere. That's for sure. And I'll tell you what, you would get a lot of pinging and knocking. You get like rattling noises coming out of the engine. See this? We're not going anywhere at this specific moment in time frozen. Everything is lined up straight down. We're not going anywhere. But now I'll tell you what, there's going to be some engineers that come along and recognize the inherent problems that we have with, well, the situation. They know how to overcome it, and we're going to talk about connecting rod or we're going to talk about wrist pin offset shortly or eventually. All right, good stuff. So I'll tell you what, and again, Donut has this in there, force time distance, I'll tell you what, maximum torque. This dimension, or the stroke of the engine, a longer stroke engine is going to give us more torque. All right, and that's going to be a lesson of, you know, if you want to get the full understanding, you got to become a math whiz. I salute you. We'll continue on. Now again, Donut, he in his video, absolutely great. We're going to list 330 pounds, 100 feet, because he's overcoming gravity. That would be a way to measure it, going back over old James Watt. Now, by the way, then how much work was done? 330 pounds times 100 feet, 33,000 pounds, right? But what was the rate divided by 1 minute? 100 feet multiplied by 330 pounds, that's 330 foot-pounds there of work, but divided by this gives us actually 1 horsepower. It's per minute. And of course, if it took 2 minutes to do it, he'd have only half the horsepower, or he'd have only half a horsepower. And if he did it in just 30 seconds, I think he'd have 2 horsepower. So thank you, Donut, for returning to James Watt and where all this horsepower talk got started in the first place. All right, and now he also, and that's Donut himself there. You can see the T-shirt. Great job again. I thank you. And yeah, I mean, I just used it because I can. All right, now, Donut also talks about using a chassis or an engine dyno. And he also talks about the gearing. And here's what this is going to come down to. We're going to find out, I'll tell you, if you had something like a 2-speed trans, you might want to shift gears somewhere around here. Then when you shift into the higher gear, you know, when we're accelerating, we upshift, right? We go from first to second. All right, now, if we got like a two-speed trans, there's going to be a big drop in RPM, and we'll come way down to here in terms of developing torque and how much our rate of acceleration we're going to have. If you have a six-speed trans, you're going to be able to keep the operating range right up in here. You lose less RPM between gears when you upshift. Of course, when you rev way up over here, bang, you change gears, RPM drops a little, you come back up. You'd be operating this range. Your peak acceleration is going to be, better. And that's really what the issue is about as we bang gears going down the strip. Now, additionally, what I like, why I want to thank Donut for mentioning the chassis and the engine dynos is just so you know that electricity can be used to operate a starter motor to make your engine turn. But that same electricity, and because of the law of electrostatics, can also be used to recharge your batteries. It can be used to measure horsepower, make an engine slow down. It can be used like as an electric brake to make the car slow down. It's called regenerative braking, where you don't even have to wear out your brake pads yet. All right, and actually the first law of electrostatics, you got it right here, is opposites attract. And the other half of that law is likes repel. Sometimes an electric motor is known as an electric repulsion motor because as you have a field and an armature that'll spin, repelling one another, that armature keeps turning. But the same wiring can be turned around to put a load on an engine. And what you'll find out that horsepower is measured where they put a real load. You got the engine at wide open throttle and you try to get more RPM out of it. But when it won't gain any more RPM, I'll tell you what, right at that point, you're measuring the horsepower that the engine is making for any given RPM. And all that can be done with electricities on an engine dyno or a chassis dyno. Let's click on. Now, also, if we're going to be talking about horsepower, you may want to know the difference between gross and net horsepower. Gross horsepower, manufacturers would take an engine and they would put it on an engine dyno. So it's not even in the car. And I'll tell you what, they would disconnect. It didn't even have to drive a water pump. It didn't have to drive an alternator. And they would run that engine up with full power, and it ain't even operating any of the accessories that you normally see attached to the front of an engine. So that would be the gross horsepower, and they would, use that for advertising. Now, the net horsepower would be the horsepower they got out of the engine with everything hooked up, including, let's say, the oil pump. Now, I'll tell you what, you're not going to want to run an engine without an oil pump. See, so, but can there be such things as an electrically driven oil pump? Well, actually, of course, yes, you could. But keep in mind, driving an oil pump, which pushes liquid through an engine, is going to provide like resistance. The oil pump is hard to turn. You get a heavy motor oil, and let's say you're trying to turn the oil pump, you're assembling the engine, it's on an engine stand, and you take a thing called breaker bar or a speed bar or speeder, and you're trying to get that oil pump to turn, you could feel the resistance. It's actually hard to turn. I mean, same thing like your water pump. The alternator that makes all that energy, well, I'll tell you what, when that alternator's operational, it's actually hard to turn. That's why they got to have a tight belt that'll keep it going. So if you measure it with all the stuff that should be there hooked up, your net horsepower is going to be less. And if you read this article from 8 Up with a Motor there, he goes into a lot of the BS that went on. And so not only, like James Watt, who started out with advertising issues about horsepower, and Henry Ford, I tell you what, it still goes on. It went on in the 60s, went on in the 70s. How about the political climate? And the insurance companies come along and say, we are sick and tired of these high horsepower cars causing these fatal accidents. Because I'll tell you, back in the 50s and 60s, people were nuts with this drag racing and chicken racing and stuff like this on the street. There was, we had James Dean running around, all kinds of like great exercises and stupidity. And, hey, what can I tell you? We don't want to insure anything that's got high horsepower. So they would just drop they come out with funny horsepower ratings there too. All right. So again, and also this thing, by the way, is a turbocharger, and the idea of the turbocharger, you got exhaust gases coming out of that engine. And they are going from well, I'll tell you what, they're moving pretty damn fast, and they got energy in them because they're hot, and they're going to spin a wheel. And that wheel is attached on a shaft to another wheel that is actually going to be spinning and forcing more air into the engine. So a turbocharger actually just utilizes exhaust gases that would have went to waste to pump more air into an engine. Now, on the other hand, a supercharger, well, we'll see if we come across a supercharger. Well, right there's a supercharger, yeah. Now, this supercharger, look at the size of that belt. How to drive this thing called the Root supercharger. Let me tell you, the supercharger, while it forces more air into the engine, which means more horsepower is available if you're going to open the throttle, that thing got hard to turn, put a real load on the engine. So, hey, so much for that. By the way, air in, air out, these were tuned headers. Look at how short these are. There's the ultimate in tuning. Tell you what, there's no real resistance there. The engine's done with it. Out it goes. All right, let's continue on. Now, this guy was also great, and he is explaining why more horsepower wins all the time. So, if you got more horsepower, what he is explaining, see, what gives us the fastest acceleration rate? And that's the real issue. So if you may find that, more horsepower, when you've got a lot of gearing going for you, that engine can operate at high RPM. I'll tell you what, it's the peak power that really wins the drag race, because at peak power, that's when we additionally make the most foot-pounds or power being applied to the shafts that we want to turn. And this guy does a real good job of explaining it. And tell you what, we're at an hour and 15 minutes here. So I'm going to keep moving on because we still got a way to go to finish up this dissertation on horsepower. Click O. Well, to try to get a feel for what this torque thing is about, try pedaling a bicycle. You'll learn something when you push it on the pedals and the crank there. Try opening a door at the wrong angle. Think about when you're opening a door, how you're doing it, where you put, which way, what direction you're putting pressure on the door to open. Play with a revolving door to get the appropriate effects. How about the bicycle stop? You want to get going. Experiment, get a feel for what you got to do to get it going. All right? I'll tell you. I always find it. I love riding a bicycle. I hope the weather gets warm and now that I'm not as blimp as I used to be. You know, hey, maybe you'll see me over there in one of our beautiful parks. All right, well, let's see now. Explaining the process from this diagram. If you're going to be a horsepower lover, well, let's see if we can read this diagram. Now, for all intents and purposes, our intake is going to be open as we are still on, or we're on the exhaust stroke, and we are approaching top dead center. The intake valve's going to have inertia. We got to get it open along with the air coming in. We open the intake valve, and now over here we are at atmospheric pressure, or maybe even a little less. We can still have, if we're not a wide open throttle, I'll tell you what, we got a vacuum in the intake manifold. We can spin around. Piston is going up. We are on a compression stroke. Over here, we fire the spark plug. Pressure starts developing, but now I'll tell you what, does it say TDC? It does. Right in this period here, 2 to 3, is that piston moving very much? Or is it just hovering around top dead center because the connected rod's virtually straight up? The crankshaft could be moving down below, but I'll tell you what, the piston speed is going to be very slow. The piston really ain't moving. So the piston ain't moving too much. Pressures are developing. And right around here, we're going to hope to be like a few degrees past top dead center. And we're going to want our peak pressure. Then we get our power stroke. And pistons moving down. We're going to open the exhaust valve while we're still on the power stroke. Pressures in the cylinder are going to be dropping. And then what we're going to do is on the upstroke, the piston is going to go from the downstroke there to an upstroke. And we're going to push the gases out. We're on the exhaust stroke. Now over here, is this telling us that the exhaust system or the exhaust process, are we pushing against atmospheric pressure? Yes, we are pushing against atmospheric pressure. If you have a muffler, you have a catalytic converter, you have an exhaust system, well, why do we want a low restriction exhaust system if you're going to make horsepower? Because if you got restrictions in the exhaust system, you'd have a lot of pressure in here. And the engine can't get those gases out. Got the idea? If we want to make power, we're going to want a fresh charge coming in with every intake stroke. But if we have exhaust back pressure, the exhaust can't get out, we'd have a lot of pressure in here. And I'll tell you what, if there's a lot of pressure in the cylinder full of, gases that were already burned, exhaust gases, that would be like virtually like recirculating the exhaust gases. And so if you want max power, you don't want restrictions of high pressure being caused by the exhaust system. We don't want those pressures to be lingering in the cylinder. All right, now let's see. I think we got most of that one. We'll continue on. Now over here, a little something about valve timing and what this. Well, I'm talking about if you want more air in, you're going to want a long duration camshaft that holds the intake and exhaust valves open a lot to let air in and out, or exhaust and let gases out. The period during which an intake valve is open, and you know that it opens before top dead center on an exhaust stroke, and the exhaust valve did not finish closing until after the intake stroke began. Now, you know in a four-stroke cycle, the piston goes up the top dead center twice. Once between the compression and power strokes, both valves are closed. You go all kinds of pressure. But then it returns to top dead center when? Between the exhaust and intake strokes. Now, a real diagnostician, a real mechanic knows that he can look at the position of the piston and the intake and exhaust valves. And if he finds that the intake valve is open a little bit and the exhaust valve is nearly closed, he would know he is on the overlap period, and that, I'll tell you what, he would know where the engine is in its cycle. And you can go through the whole firing order that way to figure out if events are happening at the right time. And skilled mechanic, if an engine may have an issue with valve timing issues, you're going to do something called rock the valves. That's that's part of diagnostics and repair. We're going to click it again. So here's a little something. I think that this might be from Alpha Romeo or somebody, and all I did there is just show again this whole cam timing cycle and when the events happen, and this thing doesn't have as much overlap as the other example. Well, it's like, there we go. Let's click on. By the way, that's degrees, that's minutes. Degrees and minutes, actually, when we use, there might be 360 degrees in a circle. But I'll tell you what, when we're measuring minutes, there's only 60 minutes in a degree. Quick. Hot rod, thank you. And again, we want to reduce friction. I'll tell you what, a lot of old clunkers, we use flat tappet. Tappet, also known as a lifter or a follower, follows the lobe of the cam. Cam forces it open. Valve spring pressure is ultimately going to assure that it closes, but these things had high friction loss. There were things, this base over here is not concave, it would be convex, so in other words, it's got a little mushroom shape. That is going to help reduce some of the friction. But a roller lifter would be ideal, the way to go. So if we want horsepower, we want a high performance engine, you're going to want roller lifters. If the engine's going to have lifters, you want rollers. Clicko, again. Now, a cheater cam. I'll tell you what a cheater cam is. At the drag strip, very often they would measure the duration of the cam. How long the valve's going to be open, because the cam pushes the valves open. So they take a reading here. What's the duration? Okay. All right. So it's what it's supposed to be. What's the lift? They take a reading here. But this is a cheater cam because you see, this cam, it opens faster, it closes later. All of that equals more time the valve is open. So that might be like a cheater cam. And would people actually plot the difference on graphs? You know, we had dial indicators, or freaking measure all this crap, you know, about what it's going to do. So a cheater. The engine, you wouldn't hear a lope, really. A little, but all right, but again, there were things called cheater cams. Get a little more horsepower. Now, if you got a race cam in the engine, you're going to hear it in idle, boom, 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 and the engine won't have the vacuum that it should have in idle. Let's continue on. Well, all right, we want to get air on the pipe. So on the pipe is actually an expression from British racing machines, the Brits. Hey, get on the pipe. If you're on the pipe, just like if somebody knew how to play the bagpipes or the organ or whatever, it really sounds good. When that engine's really screaming and you've got your exhaust headers at the right length and you got your intake manifold all at the right length. Now here we go. This guy was my hero when I was a kid. Dino Don Nixon. I was a Ford guy. I love the Fords. I had a 428 Cobra Jet. There's his tuned a Ram intake manifold, very short for high RPM operation. There's his big 4-barrel carburetors, 2 of them. There's his Venturis, all right? And they had a lot to do with how well he atomized the fuel, and that meant, you know, how much power. And actually, this engine would run better with slightly smaller carburetors that actually had finer Venturis in them that was doing a better job of what? Atomizing the fuel, and he'd get more power with the slightly smaller carburetors. All right, but at any rate, so this was real stuff back in the day, like 1970. Ooh, this was hot. Why? Because it had like an overhead cam, and over here, again, on the pipe, these things were hill boards, no air restrictions. You want power, we don't want to restrict air. We want it to get in. Boom, there it is. Hillboard fuel injectors. Wow, wonderful. Look at how short those pipes are. No restrictions in the exhaust. We continue on. Now, these were cylinder heads from that famous Ford single overhead cam of the late 60s. Hemispherical combustion chamber. Intake was this side, air shoots right in that way. Easy enough to get out right there. Boom, out. Even better, 4 valves per cylinder. We've talked about that already. 2 intakes, 2 exhausts. Again, it was easier for the valve tray to control the opening and closing of these lighter weight valves because they were a little smaller. We continue on. These people, thank you, Burn Stainless. Now, I'll tell you what they did was they provide a nice little dissertation that explains, if you go to this website here, that explains if you've got the length of your headers just right, you could actually get a low pressure wave. Well, imagine exhaust, it's going down a pipe. Something fast moving goes by. Is there something that happens in its wake? Yeah, well, usually in its wake there's a vacuum or an emptiness or a void. And actually, a pressure wave going down exhaust pipe leaves behind it a slight vacuum. And the idea is you want the peak of that vacuum to appear way back up at the cylinder right as the intake valve is just beginning to open during that overlap period. And if you've got a low pressure in your exhaust right when that intake valve begins to open, you're going to suck in, or more air is going to go into that cylinder on the intake stroke. All right. So the right length pipes gives you a low pressure wave at the exhaust port right when the intake opens. We'll go on. I'll tell you what. I'm going to thank Hot Rod. Here we are. We're on the engine stand. They're testing one of these. These things are glowing because they'd warm the engine up, and then on an engine dyno, they want to get horsepower out of it. Those things are cherry red. Fuel control on these old engines could be anywhere, and I got to tell you, that's part of the exhaust system getting so red. When they made these headers out of headers were the cast iron and heavy, I'll tell you, because the factory knew what was happening at sustained load there under your hood, and we're lucky we didn't get a lot of car fires or whatever you want to call it. Let's continue on. Now, high performance engine. Yesterday's engine, we had a camshaft, we had a lifter that we looked at briefly, we had a push rod, you had a rocker arm, a pivot for the rocker arm, and then the rocker arm, when the cam would come around and push everything up, it would pivot down this way, push the valve open. Well, I'll tell you what, with all this stuff, back and forth, back and forth, back and forth, forget about it, I'll tell you. We would break, bend, push rods all the time. Extreme, all kinds of opening. Now the geometry's not right, and we're pushing it this way, we're pushing the wrong way. All I can tell you is these parts would break left and right when we went into high lift cams, long duration cams, because all the angles would be pushed to extremes. So these things, I'll tell you what, I didn't like them too much. Stuff would break left and right. To close a valve quickly at high RPM, you might take a spring that was designed to provide 200 pounds of pressure as the original. Now you got a valve spring that provides 400 pounds of pressure when it's open. And the next thing you know, sometimes we'd actually crack the cast iron where these valve springs would sit. So in other words, a lousy design. I'll tell you what, I am not a push rod fan. Now this engine was described as overhead valve. All right, it was overhead valve. Let's continue on. Now, there's the mechanism I was talking about, and again, we'd want to get, if you got a flat lifter here, you're going to want a roller cam. Up here, there's the rocker arm I was talking about. Well, I tell you what, this is a roller lifter going down here. We would also want roller rocker arms. that would diminish some of the breakage and reduce friction. Let's click on. All right, now that 427 overhead camber, it had uh, lightweight valves, sodium-filled exhaust valves to carry heat away from the seat. The things will get so. All right, and again, what kind of valves do we want? Well, we want them big, but we're going to want them to be low mass, real lightweight. And does that mean an expense? Yeah, they're expensive. All right, lightweight permits high RPM operation. Over here, this is where the cab sat, uh, and we'll just a problem with uh, the camshaft of that overhead valve V8. Uh, the cab was being driven up here, and by the time you would push on, you'd have all these springs, the length of the engine, pushing down on that one camshaft. And by the time you got to the end of the block, the camshaft had actually twisted at the back, and the valve timing at the back of the engine, away from the front where the timing chain was, would actually be late because the cam would twist. So right there, that lost horsepower. And I'll tell you, if you're going to be a winner, you don't want to lose horsepower. So what can we do to assure better valve timing throughout throughout the engine? Tell you what, instead of one cam, we could have two. One here, one on the other side. And better than that, how about a dual overhead cam? All right, how about 4 camshafts? That will reduce the loading or the twisting of the camshaft and make it more accurate, or it'll perform more according to design. Let's click on. All right, so by the way, just as a curiosity item, on that overhead camber, these cams were not interchangeable. That came up here. Yeah, there's an example of, all right, a needle rocker arm, needle bearing rocker arms. These rocker arms actually had needle bearings right in here to reduce friction. That simple. And there's another roller on it. So in other words, needle bearings, roller bearings all over the place, all that stuff is going to reduce friction. That means more power, maybe less breakage. And here we are with uh, uh, the cam and the rocker arms and everything all assembled there on our, this thing here is a rocker arm shaft that those rocker arms pivoted on. This is really like a freaking great design. And I got to tell you, it's a young hot rod. Oh my God. Oh, I desired one of these engines. All right. We'll continue on. So in other words, now, dual overhead cam, again, I really think is a wonderful way to go. And we got plenty of the factory cars. I tell you, the engines that they built today, absolutely wonderful compared to what we had. All right, and all right. So if you're going to have 4 valves per cylinder, uh, how do you lift? How do you open 2 exhaust valves at the same time? Well, that's one of the ways that it might be done. Right here, this is a high performance rocker arm. Right? See, we're gonna have your needle bearings out here, your roller there. Whoop-de-doo. Low friction. All right, now next up, it's very important to have a good bottom end. There's nothing like a nice bottom end. Everybody likes a nice bottom end. And if we're going to be making all of this power, uh, on these power strokes and pushing down so hard with such high compression, are you going to want an engine that does not distort down in the crankcase where the crankshaft is here. Now, these designs are called like Y-block engines because the casting of these V8s exceeds down past the crankshaft center line for extra rigidity. So these are good sides. So in other words, we're going to want a strong bottom end. It's that simple. We want the bottom of the engine to be strong. Now, this design, now you see, so this is a Y block design, and over here, these are called cross-bolted mains. See, because not only do the main caps bolt down this way, but they're actually going to bolt in from the side. That holds, at least that holds a part of the engine right in place, so it's where it's supposed to be. Now, this design does not have that, and, heaven help them, something like this is going to twist all over the place. We'll continue on. Now, next up, this here from Uncle Tony's Garage. I believe this guy's a Jersey boy. But at any rate, very interesting stuff. Windage tray. Now, I'm going to challenge you to take next time you finish a bottle of water in a plastic stuff, put a little, like a mouthful of water back into it, or, a couple of ounces, and then go back and forth like this. Whoops. Oh, there's the camera. Whoop, whoop. And what you'll see is when you take off with it, that the water that was laying flat on the bottom, or you laid it on its side, whoop, that it stands up. So when, in other words, so when we would take launch a car off the line, actually the oil that was down in the crankcase, now there's a crankcase down here, and Tony is going to fit that down in here before he fills it up with oil, and that'll prevent the oil from standing up when you accelerate. So just play with a bottle of water, and you'll see what I mean. Lay it on its side, whoop, go like that real quick with it if you got just an ounce or two left in it, and you'll see the water stand up real fast. Let's see, let's continue on. Now this guy, that's Dino Don, actually coming off the line when you had a Comet, and to come off the line and really accelerate fast, because besides your horsepower, you want to do this real fast. Spin the engine at like 7,000 RPM while you're in neutral, and then you would pop the clutch. And all the energy, well, I'll tell you what, you don't want to catch 90 pounds of steel spinning at 7,000 RPM, because it's going to go through you like a buzzsaw. But you let the clutch up, bang, all of that stuff is going to start getting the gears, everything, the drivetrain in motion, and that car's going to, the front of it's going to pop up like, boop, it's going to go like that. We don't want the oil in the engine to now stand up at the back and do what? Rob horsepower. So when we would launch a car off the line, you wanted to have a windage tray or a baffle plate that would prevent oil from standing up at the back of the engine. And that's what that is about. And it's also, the idea was to bring this up, actually your flywheels can be used to effectively store energy. Spin them fast, then you engage them, and you're going to get something moving. All right, now, additionally, you don't want your hot rod engine to break. Remember, at this point, we're flowing all this air, and that means burning all this fuel. A good crankshaft is going to be forged. You don't want a cast iron crankshaft. It's going to be cross-drilled so that you got plenty of oil getting all your bearings, and you can even hollow it out right in this section here. And instead of having just a forged steel in there, that can be hollowed out, because actually the shell, it is that be plenty of strength there if it is forged rather than cast iron. And of course, this is the back of the crankshaft. That's where your bolt, your flywheel will go on the back of the crankshaft. But again, you want forged crankshafts, cross-drilled, good stuff. All right, now let's see. You should also know an expression. Now, by the way, stroking an engine, it can get involved. If you're going to stroke an engine, if you're going to make the up and down, if you're going to make the up and down longer, that means at any given RPM, when the piston's going from up to down and back and forth, it's going to move faster. And if that piston is moving up and down real fast, it's developing more inertia, and that means it's going to try to rip itself all apart. So, additionally, a longer stroke engine, it'll make more torque, but because the connected rod angles have to be so great, and the high piston speed, it's harder to get the high RPM without breaking the engine apart. So you might, as we try to add cubic inches to our engine because we want to flow more air, are we going to have an over-square engine where the bore is greater than the stroke? Well, I'll tell you what, that's usually the case. Over-square engines, bore is greater than the stroke. They usually can rev higher because they have less stress from inertia, but they do develop less torque. But they are able to actually make more horsepower faster. And then what we're going to do is we're going to utilize the gearing to make up for the loss of torque. If you want understroke, you're going to have a long stroke. The stroke is bigger than the bore. You'll have a lot of torque available at low RPM. And now, by the way, there's a little arrow down here. What the hell is all that about? That little arrow is that is supposed to go toward the front of the engine. Whichever cylinder you put in, that's supposed to go to the front of the engine. And I'll tell you why. Well, I ain't going to tell you why yet. Look, these heavy-duty, big pistons, they're for a diesel. Diesels have static compression ratios in this range, 20 or 25 to 1. Typical gas engine, 8 or 12. And I'll tell you what limits us on the gasoline is often the octane rating of the fuel, especially for the street engine. By the way, these are wrist pins. They go right in here, and the connected rod is going to, connect that way. These little circlips, these C-clips, they go in here to stop the wrist pin from coming out either end. That's a pop-up piston. That's called a dome over there. The bottom groove is for the oil ring. The upper two is for compression rings. Let's clip on the diesel. Look, the diesel is fuel throttled. I just think everybody should know about that. Diesel ignition timing is not timed by a spark. It's not done with a spark plug. Diesel ignition timing, tell you what happens. The pressure is so high inside the cylinders on our diesel that as soon as you start squirting or pushing in at very high pressure, the diesel fuel, what happens to it? It begins to burn. See, so diesel fuel does not have to worry about octane rating. Octane rating is something like gasolines and is designed to let you know how much the fuel will resist while self-detonation. But with diesel fuel, the whole idea is as soon as the fuel injector opens, as that piston is approaching top dead center on a compression stroke, it starts to burn. All right, so ignition timing in a diesel Well, I'll tell you what, it compression ignition, and as soon as the fuel is injected, it starts to burn. It does take time, and I'll tell you what, then piston and everything rolls, crankshaft and all rolls past up dead center, and you're on your way to a happy power stroke. Let's continue on. All right, now this guy is absolutely brilliant, driving for answers. Great, absolute great stuff. He is going to talk about wrist pin offset and how it reduces side thrust on the piston. So we're going to play a game by not having this here wrist pin right dead center in the piston. Instead, we're going to move it off center, and that is going to reduce the amount of side thrust. In other words, the degree to which the skirt of the piston is slammed against the cylinder wall to go like effectively nowhere. So I'll tell you what, because of wrist pin offset, we get less noise out of modern engines, and we get more power. And of course, we have less friction. And it also does some help to get us a little more torque actually applied to this crankshaft that we want to spin. Guy does a great job of explaining it. All right, so I'm just all right. Now also, again, driver 61 does. This is a Formula One piston. Over here, this is like a street piston, and it looks like a relatively modern vehicle here. Probably 4 valves per cylinder. He talks about how this super duper, see what the piston's supposed to do is basically just work with the applied forces. And so for that, all you need is a dome. And the skirt, what's it there for? It's to keep the piston straight in the cylinder so it doesn't just spin around and go to nowhere. And I tell you, this is a great video here on what it takes to make a Formula One piston. And now we're going to continue on. Next up is an article. If you go here, I'm sure you'll love it. It compares F1 engines. Now, maybe you've seen those Formula cars, or maybe you heard them on TV. They're the ones going, wow, 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 wow. They're going like, wow, wow. Those things are really screaming and flying. And I'll tell you what, he compares those engines to Winston Cup NASCAR engines. And so you got 147 cubic inches in the F1 engines that he was talking about, and you got a maximum of 358 on the Winston Cup engines. Let me click it. Oh, brake mean effective power. I'd like to know what that is. So that's the average pressure being applied, is a way of calculating horsepower mathematically, but you'd have to know what how much pressure is being applied on an average. I got to tell you, you got to have all kinds of equipment for that. Peak power. Well, I'll tell you what. Your car probably has a tachometer on it. F1, those engines are getting revved to close to 20,000 RPM. I'll tell you, if you go to the drag race, you listen to the motorcycles, they can crank out pretty fast too, but 20,000 RPM is hot shit. And I'll tell you what, the Winston Cup engines, even those engines got push rods. I can't freaking believe it. They are revving those things over 9,000 RPM. So, you know, that's all real hot stuff. And they're talking about some of these piston speeds. Imagine moving at 8,000 feet per minute and then changing direction. So there are forces trying to rip these things apart. It's just interesting stuff. Let's see. Well, again, red lines, 20 grand, 10,000 RPM, all kinds of stats on what the hottest stuff is doing, naturally inspired. Those rails can make like 2,000 RPM, 2,000 horsepower, I believe. All right, now, by the way, you should know what static compression ratio is. Simply, you measure the volume of the cylinder when the piston's all the way down, because, again, we talked about displacement. More displacement, you can pump more air. Run the piston to top dead center, see what the volume is there. Divide one into the other. Now you know what the displacement is of the cylinder. Multiply that by the, excuse me, you know what the compression ratio is. All right. Now, again, we're getting near the end. Combustion. Make sure that we appreciate combustion snapping together of oxygen and hydrogen molecules. It is not an explosion. See, this is a flame front and pressure waves growing. That is what is happening here, all right? It's growing. It's not an explosion. It's a developing pressure and flame front. Again, the purpose of an explosion is to break something. The purpose of combustion is to develop a working force that's going to push, well, for our purposes, that is going to suit our purpose, which is pushing the piston down the cylinder. We're going to continue on. Now, burning takes time. So and ideally, again, you're going to want combustion peak pressures to occur somewhere in the range of 15, 17 degrees after top dead center. And it takes real time. Now, for any given air-fuel ratio, fuel condition, and load, if you're at low RPM, well, the crankshaft is not going to turn, too far at low RPM. So you might begin the process. You might fire the spark plug at 18 degrees before top dead center. If you rev the engine up, basically all the other factors are going to be the same. Well, then you're going to have to advance the ignition timing. And so now we might find the ignition timing way up to 40 degrees before top dead center if we were checking it with a timing light. But in either case, the goal is always to have peak pressures occurring 14, 18 degrees after top dead center, something like that. We click on ignition timing. Let's ask a couple questions. What happens? Engine power if ignition timing is delayed or too late. Tell you what, you would lose power because peak pressures on your power stroke would not be as high as they should be. What would happen to engine power if ignition timing was too retarded? Retarded is the same as late. So it's the same answer. Late time and retarded time is the same thing. What would happen to fuel economy if ignition timing was too retarded? All right. Engine power. Let's see. Forgive me. Brain fart. Now let's see. Fuel economy. I'll tell you what. If you're making less power, because your ignition timing ain't right. If you want to go 60 miles an hour, you got to open the throttle more. You're going to burn more fuel. So in other words, retarding the ignition timing isn't going to do you any good, isn't going to do the wallet any good. Now, what needs to be done to ignition time to achieve maximum power fuel economy? You already know. Assure the peak pressures, however you have your RPM load curve, however you assure your ignition time, we want peak pressures to be occurring 14, 18 degrees after top dead center. We'll continue on. Do we have some rules for ignition time in advance? And one guy on his computer controlled car, I don't know if he knows the math. No. Let's see. Less RPM, less ignition time in advance. Low vacuum. Now, low vacuum means you have full atmospheric pressure in the cylinder. That means your molecules are going to be packed close together. They're packed close together, that flame front is going to burn. It can spread fast. Now, on the other hand, let's have a forest fire where the molecules of the trees are far apart. If you have a high vacuum, you've got less air, fewer combustible molecules, less oxygen supporting for combustion. All the molecules, everything's further apart. And that means it's going to take more time for the fire to spread from one tree to the next. If that's the case, you need more ignition time in advance. Got it? So, all right, now, a high load, you open the throttle. High load, high charge, plenty of fuel comes in, everything's packed close together. So you need less ignition time in advance at wide open throttle. You go to the drag strip, the old timers are drag racing. How come your distributor does not have a vacuum advance mechanism? Well, that's because at the drag strip, the engine's designed for only one thing, wide open throttle. That means all you need is an RPM, a centrifugal advance. As the engine RPM goes up, it'll advance. Now, what will happen if we over-advance the ignition timing? I'll tell you what, you'll be lucky if you start hearing the engine rattle, if it's starting to, sound like a can full of marbles or ball bearings. Uh-oh, you might break that engine. You don't want to over-advance your ignition timing. If you're a drag racer or you're in any race, you want maximum permittable advance to get full pressure. You see, you're over advanced if you make the engine pig. So you got to come back just a little bit from there. But if you over advance the ignition timing, you break the engine. See, so you're always pushing that engine. Peak pressures are what you're really shooting for. But if you don't get the peak pressures, because you didn't advance it enough, you're losing horsepower. If you go too far, well, then you break the engine. All right, now, different fuels got different burn rates. And, you should be aware of that. Now, over here, let's see, one of these is nitro right here. No markings on it. You could use methanol. I think some of the Formula One cars, I think they used to run methanol, I forget. Isooctane is gasoline. All right, and so we see that the air-fuel ratio affects what the ignition timing should be. Now, keep in mind, you see, you have to know, you have to be aware of that. If you built your engine, it's capable of all kinds of stuff. The bottom end won't break. You got low friction parts. You got sturdy parts. All the rest of this. Now we have to tune it for maximum power. And of course, I'll tell you what, moderately rich normally generates the most power safely for an extended period of time because if you go lean on an engine, the cylinder temperatures can skyrocket suddenly, and you find yourself burning and melting parts and breaking parts. So it's just a tad to the rich to be safe. All right, and over here, this is some, well, I'll tell you what, at night you watch these rails, and the fuel is still burning as it gets pumped out the cylinder. Uh, Clicko, now I'll tell you what, as we approach a 3 hour mark, uh, methanol, ethanol, these guys can be used as racing fuels. Look at this, they contain their own oxygen. You need oxygen to support combustion. They talk about adding that, well, I'll tell you, that for different fuels, you have to assure different amounts of fuel flow to match stoichiometric, in other words, what does a good job of burning all of that fuel. Gasoline vaporizes easily. Latent heat of vaporization, gasoline is good stuff on a cold morning. These alcohols, not so good. It would take a lot of heat to get these things ready to vaporize and play the game. On a hot day, the alcohols can create less vapor there, I'm going to say, on a hot day. Now, I know that alcohol, perfume, they put alcohol in perfume so that we can smell it, it vaporizes. All right? But gasoline develops, really vaporizes like all hell on a hot day. And that's why we have these gas caps that when you put them on, like they got to seal the vapor in because raw fuel vapors leaking into the atmosphere give us brown haze, and you got all kinds of names, urban pollution, etc. All right, now, why do we use the gasoline? And I think if I can ask, why does the fuel matter? Here's why we use gasoline. You see all those BTUs? That's why. Gasoline, for whatever goes on with the politics, it's got a lot of energy in it. That's it. All right? That is, human behavior here. Alcohol, soluble with water. Now, I'll tell you what. Gasoline will leave water in your fuel tank, which could freeze up. And then you don't get any fuel up to your fuel injectors or whatever you got if it freezes. That's Mother Nature. The alcohols are soluble. They'll combine with the water, take the water through the fuel system, and so so-called dry gas and some of this stuff, that's what it does. It makes the water and your fuel combine. It gets it out of the tank that way. Now, octane rating. We need, if we're going to be squeezing this combustible mixture together, we don't want it to self-detonate, because if it self-detonates, burns too early, you can break the engine. So we need octane rating. Now, the alcohols, they are very resistant to the self-detonation. So, sometimes we find that some alcohol being blended with the gasoline to get the octane rating up a little. So, you should know that. Octane, the ability to resist self-detonation. Let's click on. Now, next up, spark plugs. You have modified your engine you go into the racetrack. Tell you what, if you turn your stock engine, your original engine, into a real hot rod, and you continue to run with the hot spark plug, see now, here's what a spark plug's got to do. A spark plug must resist fouling at idle. Because you might, I tell you, we got some kids around here. They sit in a freaking car with an idling for like a fucking hour. Ooh, I swore. Ooh. And I'm like, why are you doing that? You're just burning gasoline. Maybe their parent pays for it. We don't want the spark plug to foul. A hot spark plug, it'll heat up and stay hot. Or now, on the other hand, if you go to wide open throttle and that spark plug, hot spark plug, is so damn hot that it turns into a glow plug, you're going to have pre-ignition or detonation, but you're going to begin your burning process too soon. You're going to ruin your engine. So a hot spark plug, it keeps the center electrode hot to resist fouling. But we don't want it to get so hot that it turns into a glow plug. Now, you're going to want to add a cold spark plug to your hot rod engine. And here's what you do. You put the cold spark plug in, and you warm your engine up, and you get out on a drag strip, and you make a run. Now, if you find any silver or anything like this, any signs of detonation on the cold plug, you got to get a colder plug. But if the plug comes out clean, and you let the engine idle briefly in the pit at the drag races, well, then it's like you're going to be okay. See, because what'll happen with the cold spark plug, it has a short heat path. When you go wide open throttle, it can dissipate all the heat that is made while you're like really right at wide open throttle there for the 10 seconds or 15, for the 10 seconds or whatever it takes to get down the drag strip. All right? So just be aware that the right spark plug lets you idle, and it lets you go wide open throttle too for an extended period of time. All right, let's click on. Now, abnormal combustion, for what it's worth. Detonation would mean pistons on the way up. You have pressure, and you got two pressure fronts beginning. One because you have fired the spark plug. The other because something happened there in the cylinder. Maybe you got a low octane fuel. Two pressure fronts meet. Bang. You're going to have too much pressure. Damage the engine. Now, pre-ignition simply means that burning starts somewhere in the cylinder before you actually fire the spark plug. What's going to happen, or if that happens, two pressure fronts, bang, you're freaking dead. And let's click another one. Again, normal combustion, smooth pressures. We're in a cylinder, somebody got some fancy equipment. The slightest bit of knock, probably tolerable. I'll tell you what, over advance your time and do something really wrong, cylinder too hot, bad design, you're going to break the engine. Let's click. And here we go, abnormal combustion. And that's no good. Broken parts, hammered away. Do we have anything else? Broken parts, holes. All right, I think that's it. And so, all I can say is free Luigi. Healthcare for all. That's the way I look at it. If we're human beings, we're all entitled to good medical care. And let's get rid of all this freaking student debt. these kids, how are they supposed to enjoy life? You know, you know, boat anchors, and let alone these freaking, you know. We repair the roof on a house because we know that we don't want the rain that could happen in the future to damage what we have. So assuring an educated America is good for America. Those who don't want education, they want to be dictators, slave owners. God bless. Enjoy. I think that's it. Thanks for listening. On a final note, ignition systems really weren't discussed because basically uh, the assurance of spark in and of itself does not add horsepower. So if an ignition system fails to deliver the spark, you lose in horsepower. But ignition systems typically don't cause a gain in horsepower. This old ignition system on a Boss 302 would fail when it got hot. And the points were set to factory specs. And it was simply that, a thing called a coil wire would get ridiculously hot. So yesterday's ignition systems had many weaknesses, especially at high RPM. We would have point float or point bounce could occur. And by the way, valve springs can float out at high RPM too, but this is actually right inside one of the distributors called a dual point distributor. So we can just briefly, here's a waveform or waveforms from an early General Motors high energy ignition, but let me say it's probably true that modern ignition systems are absolutely wonderful. They're pretty good. We've come a long way from distributorless ignitions. You know, they were pretty good when they had high energy coil packs. Now they put actually the ignition coil right on top of the spark plug, and electronics assures very accurate valve timing. So with that, let me say, goodbye. And on a final note, it seems we have reached the end. Now, to those of you who think that Trump is going to restore us to a manufacturing economy, we've always maintained some manufacturing. But you may want to take a look at how much of that wall he never built. So this is just if you really think he's going to restore us to a manufacturing economy, keep in mind that's going to require cheap labor. Now, he's got friends on Wall Street who are friends of cheap labor. I don't know that they're friends of ours. They're certainly not friends of mine. But if you really think he's going to restore or bring about a healthy manufacturing economy, there's a bridge in Brooklyn that I may be able to fix you up with. Please, get in touch. And I tell you though, Elon Musk, he touched my flag, and look at what happened to it. Ooh, it looks a little faded, a little tattered. Well, that's it. Goodbye, good luck. May your grandchildren live in a world where they're free to be themselves and speak their minds. All that remains to be seen. God bless, toodaloo, and let us pursue a better contact with HP, whether it be higher power or horsepower. Enjoy your life. Good luck. Goodbye.